So circuit board technology has been around for quite a while. I remember years ago. What's that? You know, I don't know. Who did invent circuit boards? Motorola. You talking about the works in the drawer? Boop, Quasar by Motorola. Cool, the works in the drawer. Well, great. Well, we used to work for Motorola, so, but not that particular group. No, but if you remember some back in the tube days, for some of you folks who remember those, it was basically, that's right, this you'd have these tubes that were mounted on a chassis, and then from there you'd have all these wires going everywhere. And then they came up with some other stuff called wire wrapping, and just painful. I'll show you some stuff like that. But getting into doing your circuit boards, I'm sorry?
Copper etching.
Copper, we'll get into that too. That's painful. Good old Radio Shack stuff. So let me get started on here as far as the fundamentals of printed circuit boards. Things that printed circuit boards nowadays are inexpensive. They definitely help make a much cleaner design. In the past, you would end up taking a breadboard, something like this, and then you'd hand wire it, and then, darn, wrong value resistor. I got to go change it and pop it back out again, and then you have all your wires all mangled. It's a pain in the neck. And for this, whoa, hold on, don't do that. Wire wrapping, if you can see this right here, guess what? You spent all this time hooking this all up, and then it turns out that one of the wires is crossed, going to the wrong spot. I never did wire wrapping. I saw it and just said, no, not going to do it. Just a real mess. And there's the ugly construction where you take a circuit board, a blank circuit board with just copper, and then you use that as your ground plane, and then you have your components sitting up, I guess they call it ugly duckling or whatever else, and you have your components sitting up there and make your connections that way. But if you got to make a change, it's a pain in the neck. So thank goodness for computer software, because when they first started doing circuit boards, they would have to have this big drafting board, and they would call it tape out. They would end up putting tape where the copper is supposed to be, and then other sections where there's not supposed to be any copper. Very, very painful. Nowadays, you've got free software. KiCad, KiCad, I'm going to call it KiCad. It just makes more sense to me. That is one of the free softwares. There's some other free software out there as well. There's some other ones that are more expensive, like Altium and OrCAD and some other ones. You can get a trial version and try it out, and then try it before you buy it. Altium's kind of a mid-tier price. Then you've got the Mentor graphics and all the really commercial stuff that big companies paid licenses for, really, really complex circuit board design. Some of them people have done. In fact, a good friend of mine who's a ham radio operator who also has done CAD for a number of years has done 20-layer circuit boards. We'll get into all the different layers here. Most of the time, we're going to be dealing with 1- and 2-layer circuit boards from a ham radio perspective. Sometimes 4 layers if you want to have some nice ground plane. The beauty about circuit boards versus some of these hand wiring is higher frequency operation becomes more feasible. When you had that little wire going across here, think about the stray capacitances or parasitics or anything else, that back in the olden days, those type of devices and tube transmitters and everything else, they just couldn't go real high in frequency because the leads are too long. You have to get something really shrunk down. And as I mentioned last month about surface mount technology, this allows you to really compact your design. Your whole assembly becomes much, much smaller. Like you end up seeing here. Here's some surface mount parts mixed with some leaded parts, and here's something with just leaded parts all together. But you could take this circuit right here and make it all fit in about even less than 1/4 of the size just by going the surface mount. Therefore, you have better performance for higher frequencies. It's just a much better way to go. So some things I wanted to go through as far as definitions. Before you get started into designing circuit boards, for those of you old-timers who've been doing circuit boards for years, this is old hat. But for those of you who have never done one and are intimidated by it, I'm going to give you some of the basics to get you started. There's also some really good tutorials. Thank God for YouTube. There's this one that you'll see that I've got a link to. This young lady from Australia has some really nice tutorials on KiCad. She calls it KiCad. And they're about 10 to 15 minutes long, each of them, and she goes through all the different phases of designing your circuit board, starting with the schematic and libraries and everything else. So the different part types that you typically are dealing with are surface mount or leadless parts, and then leaded parts, your old conventional parts that everybody's been using for quite a while. So that way you would use what are called plated through holes, is what you would end up putting a leaded part through. Sometimes you wouldn't plate that hole. If you just want a really simple board, you just have a one-sided board. In fact, some of the ham boards that you end up getting, little project kits. I think, Mark, that one board that you had, it didn't have plated through holes. It just had PCB runners, copper on the backside. You put your part through, you bent the lead a little bit, soldered it to that pad, and that was it. So you can have non-plated through holes for leaded parts. Plated through holes are really nice, so mechanically they hold a lot better. Your part library, for any type of CAD program that you've got to create a part library. And what that library is, it not only has the part, whether it's a resistor or maybe a 2N2222A transistor, it has the package type, it has recommended pads that you would use for either a surface mount part or the lead spacing for like a TO220 package transistor, a leaded part. All that kind of information is in there. It gives you both the electrical as well as the mechanical definitions of that particular part. That's all in the part library. Substrate, that's a base material for your circuit board, because the last thing you want is, okay, I'm going to take and put some copper on a flat sheet of paper and it's real bendable. That's a problem. Although there are substrates, and I forgot to mention that in here, there is flex circuitry, and those are meant to be bent. You'll find all of your cellular lithium-ion batteries for your cell phone, they've got some little flex circuit. You take apart an iPhone or an Android phone, there's flex circuits in there as well. That is considered to be a substrate. It's made out of either polyimide or Kapton, are the two prominent type of materials, and they're very flexible as well. The copper itself will last, they're able to bend it, and it's got a really good amount of strength, but you can also curve it around areas that a stiff circuit board wouldn't. Most of the times you want a circuit board that is mechanically stiff, so you can put all your parts in, it'll hold everything in place. Layer diagram, I'll be showing you some examples of some of this. That shows you basically all your layers and what makes up that circuit board. So you have your copper layers, you have your core material, and then you've got the different like solder mask and things like that. It may not make sense completely right now. I'll have pictures of this a little bit later. Gerber files, nothing to do with baby food. And I'm not sure who, I think it's Mr. Gerber that created them, or there was some company, maybe Gerber ended up creating them somewhere. Anyway, Gerber files, it's a PCB file that basically has all of your different layers of your board in there. It has drill drawing, the drill files, and everything. Basically, it tells the PCB manufacturer how to fabricate your board. So those are all encased in the Gerber files. If anybody has any questions, stop by all means, raise your hand, and we got microphones we can pass around as well. Drill drawing, as I just mentioned, with every circuit board, you've got to have holes in it for the most part. Especially when you have leaded parts, you got to have holes. So that drill drawing is going to show exactly where they will drill through that particular board to be able to, and it's going to be a certain size, certain XY location, because there's an origin point on your board, and then those holes are determined whether, X location this way and negative Y location here, and that's exactly where they drill a particular hole size, whether it's a 1/8 inch, ½ inch, whatever else, even really tiny 1 millimeter drill holes. The ones that are plated through, there's a whole process that you take and deposit copper in that drilled hole, and then they plate that, and then it connects the different layers, and then they put tin plating on those as well, so that way the copper, A, doesn't corrode, B, so you have something you can solder them, so they're pre-tinned. Outline, that's basically the outer edge, the real estate. You have a house that's got a certain real estate boundary. That's essentially what it is. This is where all your components are going to fit within that boundary. So that's your outline. It's a mechanical drawing. A lot of times they'll use DXF DXF files if you happen to use AutoCAD and some other different programs. But here within this KiCad program, you can actually draw your outline. Here's the size what you're going to need. Runners, those are just nothing more than circuit board traces of copper. If you take you were mentioning, Tom, was it? Were you mentioning earlier about etching your own circuit boards? Okay. So etching your own circuit boards, I remember years ago I went to Radio Shack, got that solution. You put it into this blank piece of copper and you put this etch resist on there and everything else. And painted them, whatever else. Then you put it in this bath. You have to shake it around, keep it a certain temperature. And a lot of times they weren't nice, clean edges. They were all jagged unless you were really good. But, just for the average Joe, they weren't that good. But those were still runners. And the runner thicknesses as well, you want to make sure that when you design your board, if you have a lot of current running through, guess what? You're going to have a much wider, fatter runner. Just like if you're going to use 30 gauge wire versus 16 gauge wire versus double-aught wire in your house or anything else, you want to make sure that your copper can handle the amount of current without burning up. I've seen boards as well that my son's computer, we were working on it, didn't realize that the battery, we thought we disconnected it. It was still connected somehow because one of these onboard batteries, and went to the motherboard, did something, all of a sudden, psh, well, guess what? That copper trace, gone. So that can happen. You need to make sure that your copper runners will handle the current. And we'll get into some of those definitions that they have later on in the program here. Plane, this is like a copper ground plane, just like the base of your antenna. Well, guess what? You have a power plane, you have an RF ground plane, you have a DC ground plane. Sometimes with some boards you have an AC plane versus, a primary versus a secondary for if you have an AC adapter or power supply. You have those different planes. But that's basically a large amount of copper that allows you to be able to connect a bunch of grounds to it or, distribute a lot of power through there. So you've got this power plane. But that's just basically, a majority of that is just a solid sheet of copper. Sometimes there's holes in it because you have other means to get to the other layers through what is called vias. And just like the term via means going through, that's exactly what a via does. Which is the next thing on the list. Plated through hole is another type of via, but that is definitely plated to connect one layer to the other. I've got a good example that you can clearly see where you have runners on the top layer of the board, runners on the bottom layer of the board, and you connect them through a via. So that way, if you ever try crossing a highway, a busy highway, running across, not a real good thing. It's best to go take a tunnel to get underneath there, and that's essentially what a via does. It allows you to be able to cross over a particular lane and get to your other side. Solder mask, that is especially for surface mount parts, is to prevent solder from bleeding across the whole board itself or from adjacent parts or whatever. You have this solder mask material, basically is a solder resist. It's more like a dam that prevents solder when it reflows and gets molten, that it prevents it from jumping over to the next pad, especially if you have a lot of solder. So that's the importance of having solder mask on a board. Solder pads, those are the mounting location for whether it's a leaded part or a surface mount part, and I'll show you some examples of some proper pad designs. Silk screen, this is something that really helps you to identify certain parts. You're looking at a particular board, somebody's got some project board and it's just a bunch of copper and they've got this component overlay, shows where everything is, and you're trying to figure out, is the capacitor go through this hole or that hole? If you have a silk screen, you can actually show the outline of the part. You can identify this is R1, R2, R3. It's really helpful for when you go to actually build the unit, and you'll see examples of that. Paste stencil. As I mentioned last month, one of the key things for manufacturing of a surface-mounted product is you have this squeegee of solder paste, which is almost like it's paste, and it's got solder balls and flux and everything in there, and you've got this stencil. It has little holes in it that fit right over the pads where you want to deposit solder. So you squeeze that solder paste over that stencil, and the paste goes through that stencil, sticks onto the pads. You pull the stencil back up, lo and behold, you have solder on your pads. That's what a stencil's for. It's an exact match of what your circuit board is with regards to the pads. And DRC, otherwise Design Rule Check. So any decent software is going to look for certain design rules to make sure, A, your parts are not too close together, you don't have runners that are shorting each other in the circuit. It all looks at the actual schematic, it looks at the mechanical layout to make sure you're not exceeding certain guidelines. Like for instance, if you have a part that's right on the edge of the board and you don't really want to have it on the edge of the board, because a lot of times when you go to separate the board, you can damage those pads. Yes, sir?
Doesn't like him either.
Yeah.
Does it have anything in there for capacitance or reactance between those leads and whatnot? Any
Actually,
calculations or limits or
it,
any?
not KiCad, at least not this version of KiCad, but anything like Mentor Graphics, Altium, Pads, some of these other commercial programs, yes, you can actually tell the impedance of a transmission line. It'll tell you about interelectrode capacitance. You have to put those properties in there, but you can model that, yes. Is it typically done? No, except for doing high frequency designs, like for instance, when they design the iPhone or anything like that, really compact. You want to take a look to make sure that your runners, especially, for instance, I did a pager years ago that had a multiplier circuit, what we call B double plus, very noisy signal, and it was right next to an antenna. And those are just some things that you could have modeled that and said, oh, wait, here's this runner. But what we did is we highlighted on the actual program, you could see the layout and say, okay, let me click on this particular runner, this bus, this node, and it'll highlight, here's where this is all a common circuit all the way across. And I'm like, dang, that's horrible. So we ended up redesigning it such it was all nice and compact and filtered and everything else. And then the problem went away, because when we first hooked it up, it just killed the receiver sensitivity. So yes, they will do that. That's more complex, more expensive programs that do all that RF analysis. Okay. And then the PCB materials. The most common one out there is called FR4, fire retardant material. It's a fiberglass resin. And most any of the boards, Mark, the board you have there is definitely an FR4, especially that big green one you have there. If you want to, Mark, you want to hold that board up? No, your big green board that you're showing me?
This is green too.
Oh, yeah, there you go. That's FR4, and the green is actually the color of the solder mask that's on there. But that stiffness of that board, that's your typical FR4 board. There are different materials of FR4 that go very much higher in frequency. There's Teflon, which is a really good, that's fine. There's Teflon, which is really good for microwave products. Some really cheap stuff, if you want to go the real cheap route, like for certain power supplies, they use paper. It's not like paper, but it's a paper laminate. And it's stiffened up with glue and stuff like that and other resins. But it's relatively inexpensive. There's some other ones that also have thermal properties to be able to conduct and handle heat a lot better. So the different circuit boards, the materials will have different properties depending on what you want. But like I said, the most common FR4, that's what you end up doing and using. So this one right here, if you take a look when you look at the handout later on at your leisure, you'll see there's even some more detail with regards to the type of PCB materials, and this is just a limited set. There's so many different types of materials that are special quality stuff that gives you really good consistency for RF designs that you typically want to go to that. For your standard designs, audio circuits and things like that, power supplies, nothing critical there. Now, Gerber file, what that allows you to do, it looks at all the layers, combines with drill drawings and everything else. So you can see with this blue is going to be one particular, typically a ground plane of one side, and then this red right here is one of the other layers. Sometimes, though, this blue, depends how it's highlighted and how it's defined. This just could be the background substrate material. But in this particular case, what I'm seeing here, this blue, in fact, yeah, this is going to be the bottom trace. I can tell you that right now. Because here, this red, this is the top layer, and you see where your components go. And lo and behold, you got this blue runner down here. because it's this black here is where the copper has been removed. And this via hole here, and this via, it's a shame. Whoa, that's a shame that wasn't even showing up. So I'll show you right here. So here, this blue, that's going to be the bottom layer. The red is going to be the top layer. And you see there's a runner that's hidden underneath here. And the black right there is where the copper has been removed. Same here as well. And what a via hole allows you to do, if I'm going to get this lead and I got to connect this to here, guess what? I got this big runner in the way. How do I get around that? You put a via, pop a via through, you put another runner on the other side, and then bring it back up over here. So now this pad is connected to that pad through two via holes. Whoa. So that allows you to do that. So here, this is an SOIC, an 8-pin SOIC that's sitting on the top. You've got these are the pads for that SOIC. These are the pads for these resistors. What's not shown here is the solder mask, but typically the solder mask will either be right on the edge here or slightly outside of that. So where you're going to deposit solder, everywhere you see this pink, that's where solder gets deposited with the stencil. Let me see what else with this. Oh, and what you see here as far as the circuit symbols, a lot of times this is a silk screen. Not only is this in the program that basically tell you where these are, but this a lot of times will be printed on the circuit board with a white ink or what other color they end up using. Typically it's white. And if you ever done your own t-shirts, tie-dyes or whatever else, and you print stuff on t-shirts, same process. You just screen that ink right on there, and that's how they identify all these different things, plus signs, outlines, and everything else. Any questions about that? All right. Drill drawing. This looks a little muddled up, but what's going to end up happening here, you have an origin. This drill drawing is going to show you the dimensions of the board, going to show any special cutouts, and then these are all your different drills. And you see here, it shows the total number of holes here. There's a whole pile of these that are just the plain pluses. And that particular hole it's a plated through hole, and this one shows it's a 10 size drill billet. That's not going to be 10 millimeters. That may be 10 mils. I think this will be in terms of mils, or thousandths of an inch. So it'll be 10 mils, 24 mils, 14 mils. There's a whole pile of them, so they drill through there. Some of them are plated, some of them are not. So all these different holes get drilled, and some of them are different sizes. So you got a few of these, one of each, 1/16. Typically those are, well, that one is not plated, this one is. A lot of times you'll have corners that'll be considered tooling holes that are meant for when you put it into a test fixture. It allows you to be able to drop that board in, centered up correctly, and then you have pogo pins that'll contact specifically where you need to measure, the electrical circuit. But this is what a drill drawing provides, and this is usually like sometimes it spits out in an Excel file as well that'll have all the XY dimensions. But this really shows you, for these symbols, it shows you and defines what kind of holes are drilled. This is what the PCB manufacturer or the fabrication house, this is what they use. Solder mask, as you saw green on that particular board. The solder mask in this case, you see now they've taken, those are the pads, those are tin plated pads of copper. And you see the copper here where black is, that's where the copper is etched away. This is also a photolithography process. So what happens is they put this photoresist onto the copper, and they run it through this acid bath that eats away the copper where that resist is not there. Where the resist is, the copper stays, and then they wipe that resist off. And then they expose the copper, and they put the solder mask on next. And one of the last things to do is called a hot air leveling tin plating. And there's some other ones, sometimes they'll put silver plating, basically to keep the copper from corroding, because it doesn't take long for that copper to start turning and oxidizing, so when you try to solder on it, it's not going to solder real well. So they want to tin it or silver plate it, something, and there's some other stuff that they've been able to put on that when you run it through heat, it evaporates and then allows you to plate directly to the copper. But I find tin plating works great, lasts for a long time, at least for amateur radio use. So, and you can also see kind of a 3D drawing. In this case, there's your pad of copper. Sometimes they have the solder mask actually cover up to shrink that pad size down. Other times they'll have voids around the pad. But that solder, it prevents solder from leaching over because like these particular pads right now, there's no mask in between these. This is ground. This goes somewhere else. This doesn't seem to go anywhere. So if anything, these two pads, you could have an issue where you might have a short circuit. If you have too much solder, you could have a short circuit between those. I'll just stand up front with the mouse. So as far as the circuit boards, single layer circuit board, Mark, that one board you had, I believe, was a single layer. So it's just FR4 material here, copper, and it didn't even have solder mask, I don't believe. It was just straight copper for your Back to the Future board. So that's a very simple board, very inexpensive, very useful though. And then you have the double layer circuit boards, like I showed that one feature where you have a top layer and a bottom layer. This is all copper right here, and then you have solder masks top and bottom. And you can see here, this is typically what a via hole actually does. So you can see the different layers. Here's your core. The prepreg is merely an insulation, a dielectric insulation that prevents the copper from shorting out between different layers. It separates the layers. But here you've got a copper runner up on top of the board, get the via hole going through, and then they add copper during their plating process that now connects here between the top and bottom. And you can also have some that'll connect multiple layers. So when you get a multi-layer board, here you have some real fun. Here they have this ground plane layer. This via hole actually connects to ground. This one is not a ground layer. This particular one, that's VCC, or the 12 volts or 5 volts or whatever the positive side is. You certainly don't want these two shorting out. But this allows you to be able to go ahead and connect this, this power positive side, between the two different top and bottom layers and even the middle layers. So you got a ground plane here, you have a power plane here, allows you to be able to spread. Yes, sir. Where would you find a circuit like that? Oh, hold on.
Where would you find a circuit like that?
Oh, look at your cell phones. Your cell phones definitely multi-layers. In fact, some of them, they have what are called blind vias. So they have a via that goes down part way and connects, another via that comes here and connects multiple ways. But any type of computer motherboard, stuff like that, you'll find multiple layers for sure. Yes, sir.
When they're making the board, is it like a sandwich where they make the first layer, put the copper in, then
Yep.
glue together
They
the
do.
next layer?
Yeah, how they make this, if say this is a 4-layer board, so do layers 1 and 2 separately, layers 3 and 4 separately, and then they glue them together. And then, have the drill is already lined up because it's already predetermined and it's pretty accurate. And or sometimes they may end up drilling afterwards. Typically they drill before. It's one of the first processes they do is drill through the board. And then when they plate it through though, then it connects all these areas together as you see here. And then you have now a 4-layer board. But they don't do 4 layers at once. They do, like I said, in pairs. So you have layers 1 and 2 are done as a separate board. Layer 3 and 4, 5 and 6, 7 and 8, however many layers you have, they're always done in pairs. And then they're married up and then connected and glued together. And then you have your via holes all line up. And there's a cool plating process. There used to be a place called Photo Circuits down in Fayetteville. Huge operation. I mean, huge. And I got to walk through this whole factory of how they, start with the lithography process and then go through and take this big sheet of copper circuit board, and they ran through and came out with a completed circuit board on the other end. Routing and everything else that they did. They had to have these routers, just like you route wood. they route the edges of the circuit boards to cut them out to particular size. I didn't go over that kind of stuff with the boards, but it doesn't really matter because the boards that you're going to get are already going to be cut nice in size. Then we get to the definite PCB and copper thicknesses. The ones I have in bold are your most common English versions. 062 is it's vastly common. 031, if you want a thinner, flimsier board, you can get those. But primarily, you're going to find most of your boards out there 062. If you want a thicker board, if you need something that's thicker, more mechanically rigid, you can get an 093 board, and that's usually, they stack up the different board layers. Some of them are just like extra material just to go ahead and add extra thickness. And I wish I'd brought one. I have an 093 board, and it's really stiff. I needed it for what we were trying to do. There was a test fixture. Then you have your copper weights. You'll find 1/2 ounce, 1 ounce, and 2 ounce are your primary ones, typically between 1/2 ounce and 1 ounce of copper. And what that does, you can see here, the thickness of the copper. You have your same core, although the core gets a little thinner because you're still trying to achieve 062. So you end up having your copper, a thicker copper, but then you end up reducing the size of your prepreg and other sections that are in there. But you still want to come up with an 062 board. What that allows you to do is run more current. The whole idea about having a thicker copper, of course, it's more weight, it's more expensive. So, but if you need it for the current drain, because you don't want to fry something, you run with thicker copper. You typically want to do wider copper, but if you can't do wider, then you got to go thicker. So this gives you those kind of options. That's the whole idea. And when you go to get the circuit board fabbed, that's one of the questions they'll ask you. The thickness of the board, how much copper, whether you want 1/2 ounce or 1 ounce copper. And that's basically where they start off with your raw circuit board. It's got a certain amount of copper on that board to begin with. So it's going to be a certain thickness. And they show that here as far as the weight, and it shows your thicknesses and everything for the different weights of copper. So steps for creating your circuit board. First, you got to have a schematic. So either you can jot it down on paper, get that all set up ahead of time, but go ahead and get your schematic down. Choose your schematic capture program. In this case, KiCad does both schematic capture as well as circuit board layout. So you got both. So it's preferable you have the same app because that way you can talk back and forth. I know I had OrCAD at one time, and you could do schematic capture through this one part of OrCAD, and then you would lay out the board through another part of OrCAD, but they talk to each other. And that's the beauty about that. Make sure you have a part library. Most all of these programs have a part library, as I discussed earlier, and KiCad is no different. There's a part library. You can download all your common parts and even not so common parts. I mean, it's a huge library of parts, basically anything you ever need. You have to, when you start off, you'll create a new project. So give it a particular name. You'll see the example that I have. And then create your schematic. I took one, I basically stole a schematic of an audio amplifier, which would be something very useful at field day. I know some people had their headphones and want to be able to plug in and then share headphones. You can take multiples of these amplifiers, parallel them as far as the input, and then have separate drivers for the output so everybody can listen to that same radio with different headphones. Key thing, you'll see some other stuff that I added to it. I wanted to make sure there was good RF immunity as well. And there's probably some other things I may want to add to this schematic to make it even more robust RF-wise. Then you got to create a PCB outline, and then you place your parts on the circuit board. That's where it gets a little bit more dicey. You'll see some of the stuff on that. Create runners. There's things known as rats. When you first place your components down, it's just you import the parts that are from your schematic and you put them onto the circuit board. Not in a specific exact area, but kind of in a general area. And then you're going to find what they're called rats. They're basically connections. They're not runners yet. They're just connections showing, okay, point A's got to go to point B. Now I got to go ahead and put a runner in that particular area. And then that rat goes away. Because sometimes I'm going to have to cross over, and maybe I have to go to a bottom layer with some via holes to be able to connect point A to point B. And then if you have to move some parts around to get a better flow, because the one thing you don't want is stuff running all over the place. You want to have signals going as short and direct as possible. So you may end up taking a look at this and like your first layout, I don't really like that. Make some changes to go look at the flow to make sure everything looks good as you want it. So for surface mounted parts, you definitely want to have a solder mask, because otherwise you're more potential of getting shorts if you're using paste. Now, if you're just soldering surface mount parts onto pads that you're just putting down manually and you're not dealing with paste, you're dealing with wire solder, then you don't really need a mask. But the mask is free, so I just put it down. Silk screen, I definitely recommend that. It really helps you to understand where those particular parts are, identifies them, and it basically tells you. You can put your call letters on your board as well, so you know, that's mine. So you can do that as well. Then you have to generate Gerber files, because that's what the PCB manufacturer or fab house is going to need. They'll take your Gerber files, and from there, they determine everything from that. Drill drawing, outline, all the different layers. Yes? Hold on.
Are we close to being able to do this at home on a 3D printer?
If you had the material, I mean, to be able to do 3D printing of FR4 material, it's a resin. I guess you could, but then you got to be able to deposit copper. And yeah, you could do that as well. It's for pennies, you can get this done. It's probably more work and effort in just a matter of days. I mean, this one company, JLC PCB, they're based out of Hong Kong. I send stuff over to them. I have my boards back in less than a week. Oh yeah, it's fast, and they're cheap. In fact, sometimes they have discounts. I've got like 5 of these boards are about yay big, and they were like $2. It's like no brainer. So yeah, I wouldn't waste your time on that. So submit your Gerber files, pay for the boards, look for your boards come in the mail, and then when they get in the mail, have all your parts ready and go have fun. So now we're going to get into KiCad. So when you first open this up, you've got this menu up here that you see. Project files, file, this is for new files. You got your detailed here as far as schematic editor. So the 2 that I'm going to be looking at most of anything are your schematic editor. I'm not going to really edit symbols. I'm just importing the library. So do I need to edit the symbols? Not really. They've got so many of them, I'm not going to mess with it, unless you have some unique part. But if I'm a ham radio operator, I'm not going to create new unique parts. I'm just going to get what's off the shelf that I can get from DigiKey, Newark, or wherever. So, but these are the 2 main icons that you'll end up using once you get the project files opened up. So to create your project file, just like any other file, you end up clicking up here, and it pops up this menu here to go ahead and create your new project. So I have simple project for the February 2024 meeting, and I have it in a particular location. So you just give it a file name, go from there, and then the next thing you're going to do, what's going to do is going to pop up, there's my project folder, and now I've got my simple project schematic and PCB outline. So the first thing I'm going to do is click on the schematic, and you can see the suffix on there, this underscore PCB underscore SCH. Pretty easy to figure out which one is which. So I open up the schematic, there's your page. You've got all these little icons and stuff. I'm not going to go into great detail on those, but go take a look at them. You'll be able to go ahead and create your parts. In fact, here it ends up, I go to click on the library parts, and it says, oh, you need to download them. So I ended up downloading the Global Footprint library. So you can do that by the time you're done. Then I went ahead and grabbed this off the internet, just a general circuit. And between pins 1 and 8, this is actually for adjusting the frequency response. So I didn't put that in there, but I'll have to, when I update this, I'll put that in there as far as whether you, for this amplifier, what kind of frequency response you want. But it's a simple audio amplifier. You got your input, volume control, and these can go to a set of headphones. So it'll run from 6 to 12 volts. What I did here on the power supply, I added several capacitors. Besides the big electrolytic, I added a 1,000 puff cap for high frequency and a 0.01 cap for even lower frequency, just for RF bypassing on the power supply. It's possible you may even want something here on the input or on the output, probably more likely on the output so it doesn't get back in. Because you got those headphone wires and everything else, they act like antennas. So I'd recommend doing something like that. So with this, I was able to create each part, and I could show you on the, I think I had a little bit of time. I'm not going to spend a whole lot of time with that. But you could actually, I created all the parts, then you end up changing the names. So I create the general schematic. If you notice a lot of these, they'll say polarized, polarized. Those are the generic parts. There's a few of them that already changed the names, and then I went through, and this is how you do. You click on that, and this menu pops up. So the C small, I went ahead and changed the name of it. And then after it was all done, now, instead of saying C small, it says 0.47 microfarad. So you do that for all of those. You put your values in for your different parts. So there's the completed schematic. Guess what? Save it, because otherwise you'll mess up. This part, the original library part, was completely backwards, and rather than having, ground wires going all over the place, there's in the menu up here, and it doesn't show it because I don't have the parts highlighted, but you can flip the parts right or left, up, down, rotate it, and that's what I ended up doing here. I was able to rotate this one and rotate this one as well. So that way my ground side, because you got your tip and then your ground as well. I flip this one around as well for your power jack coming in. So, and also you can rotate these capacitors. They first came in, they were all vertical like this, but I wanted some horizontal. So you just click on it, rotate it 90 degrees, boom, you're ready to go. The resistors, I just put the value 10. I didn't put ohms in there or even the symbol because it just took up too much space. It's a resistor R2. I know it's 10 ohms. So for the capacitors, though, it's real important you have the voltage in there as well, so you identify that. For the ceramic caps, not so important. So I just have those. And I picked 0805 parts because those are pretty easy to put down. So you can choose the size. These are leaded components. These are surface mount components. And you'll see that when you actually pull the parts later on. Now, how many have seen the latest Mission Impossible movie? See, it's part 1. Part 2 is next week. So for the PCB layout, because we're starting to run a little bit on time, I'll show you some of the stuff I did on the schematic, but next week, bring your computers. We'll take that, and I'll show you some of the placement. I'll show you a little preview of some of the things you have to do, which is a bit more complicated. It'd take too much time for tonight. I didn't want to do that. So let me pop this over here. So here's the schematic. So if I want to add something new, see where it says place at the very top here? I can either go there or I go to this symbol over here, which add a symbol. So if I click on that, it's going to pull up a menu and say I want to go grab a capacitor or a resistor or whatever else. This is recently used items. And in this case, I'll put a C. They don't have it listed as capacitor. It's C underscore. And then you're going to see polarized or small. So I'll hit small, hit OK. There's my capacitor. Boom. So if I want to put something there, I'll end up putting a capacitor. I'm going to put it right here at this point. Then I'm going to grab this ground over here. Recently used that one. It's going to give me a ground. And then to connect them, I just click here, add a wire. So I'll click from there, click from there, click from here, and then I'm going to click up there, and boom. I've just added a capacitor. Now, if I want to go ahead and change this to get rid of this small, I'll just double click on that, change it from small to, say, 1,000 picofarad. Hit OK, boom. There you go. Now, if I don't really like, because this is real close to each other, I can take this whole thing and shift it on down. that beautiful? It's real easy to do. So once you get that down, then you can start putting these guys around. If I can also add, say, we'll do another capacitor small. And this one, I don't like the orientation, so I'm going to rotate it 90 degrees. So I can end up doing that and then moving around wherever I want. Or I can want to get rid of it, and I just go ahead and hit delete with it highlighted. Simple as that. Now, if I want to go ahead and take then that schematic, there's my board outline I created. And I have some leaded parts that I put in place. And this is, I still have to import the schematic to bring it in here, but a lot of these parts I've already associated here, like there's some 0805, forget the metric, but 0805, they have the English followed by the metric size. And there is a 2012 English size part, so you really have to be careful when you're buying certain components, whether it's a metric dimension or an English dimension. You're buying them from DigiKey because they'll have both of them on there. So they've got, this is, like I said, the surface mount part, and then I've got leaded parts here, and I've got some other parts I'm going to be placing. And then from there, you can end up taking under tools, and then it will, no, don't do that. Tools, update PCB from schematics, and give me some errors and stuff like that. But I can update the circuit board, close it, and it's starting to connect this, although it's not showing yet because there's no rats or no lines showing C2, C3 connecting to any of these other ones, but I've already changed the names of all this. You have to do the same thing. And Chuck, since you've used KiCad as well, maybe there's a faster way of doing this rather than this individual that I'm doing right now. We'll talk afterwards. Now, yep, there's a lot of stuff. I'm still learning this particular program. I've got other programs down. I've done Altium before. I'm just learning this one, but they're all very, very similar. One of the cool things here, you can also look at all your different layers as well. This is all sitting here on the side. You know, whether you have, you know, multiple layers, 1, 2, 3, 4, 5, it'll allow you to add a bunch of different layers in here so you can check and highlight whatever you end up needing. For some tutorials, and I've got this actually on a list. This young lady from Australia does a really good job, and you can see she's got a whole set of them here. How to make a PCB, episode 1, episode 2. I mean, she goes through the whole thing, creating your own footprints. I mean, really going into some good details on using this program. There's other people who have similar type stuff that just happened to work out. She was doing the stuff that I was really wanting to emphasize to y'all that was very easy, very elementary to get you started on this one. And I think she did probably one of the better jobs. So anyway, you can see she's got a whole lot of them. Yep, okay. Any questions? Yes, sir, Fisher. It's a free download. Yeah, his question was, is it a free download? Yes, it is a free download. Just do KICAD, do a Google search for that, and you'll find the download. It's free.
And it'll run on Linux, Macs, Windows. So, and you can get the source code also.
Cool.
It's there.
So it's, and if anybody else has any other programs that you'd recommend as well, I just found this was mentioned, I believe, in QST. I happened to see this and I'm like, oh, it's a good tutorial on that one. But there's a lot of tutorials on this. If you ever get lost, just open up YouTube, check out this young lady's tutorials. Like I said, she does a really good job, and go step by step. If you forget something, just back it back up again. I mean, just a good example right here. She was showing, here's the components, creating a schematic, and then doing some other things. I mean, it's just very well done. So, yes, sir. It's very. It's free. And for basic stuff you're going to do, I mean, you're not going to do a schematic that's got 10,000 parts on it. With KiCad. Wow. Okay. There you go. Any other questions? All right. Thank you, everybody.